What are we going to prove about binary search trees? Well, basically, what we're doing, why did we implement binary search trees? We wanted to implement finite maps from key values to some binding, right? Our data structure is very pretty, but it's there for a purpose, and that's the purpose. So we're going to specify its correctness with respect to these finite maps. And earlier in the week, I talked about maps in the Calc intensive. We had this type, total map. So here we're going to be using total maps. The total map function in volume 1 of Software Foundations is a map from strings to whatever values. Here, the maps.v in verified functional algorithms is from natural numbers to values. Otherwise, everything's the same. So what is a total map? A total map with range type A is simply a function from natural numbers to A. And we have some theorems about total maps. So T update eq is this theorem. If I update a map to bind X maps to V, so that gives me a new map, update MXV, and then I look up X in that map, I get V. Update and then look up at an equal key. Update and look up at an unequal key, so I update M binding X1 to V, and then I look up X2, where it's a different key value than X1, and I'll get the same thing that M would have returned on X2. Update shadow says that if I update twice at the same key, it throws away the first update. Update same says if I update at some key with the value that the map already gave for that key, then I'll get the same map back. Okay, and update permute talks about what happens if I update at X2 and then X1 versus updating at X1 and then X2, where those are different keys. And finally, if I look up something in the empty map, I get the default value. So those are the properties of total maps. And really, the binary search trees that are supposed to be implementing total maps should have similar properties. Okay. So here's what we're going to prove about binary search trees. We're going to define an abstraction relation between trees and total maps. We want to say this tree represents this total map, or this total map is the abstraction of this tree. So when you prove correctness of a data structure, what you're doing is you're proving that that data structure implements some abstract thing, and it's up to you to demonstrate an abstraction relation. Just like when you prove something by induction, it's up to you to demonstrate the induction hypothesis. And you can define any abstraction relation you like as long as it's usable to prove the properties of interest. So this abstraction relation is really part of the proof, not part of the specification of the theorem. So let's think about what would the abstraction relation be, right? We have a tree. It has a bunch of keys in it. And maybe the total map we would get is the one by inserting every one of those keys into the empty map. Seems reasonable. That could work. We'll do it that way later. Here I'm going to use a different abstraction relation. I'm going to relate E to the empty map. That seems reasonable. E represents the empty map, the one that returns the default value on every key. This tree, T, with left child L, mapping with k and v at the root and right child r, I'm going to, well, let's see. If L represents A, and if B is the abstraction of R, I'm going to combine A and B with pivot K. Right? That gives me a total map. And then I'm going to do an update. So what does combine mean? I have two total maps, M1 and M2, and a pivot value, a key. And that will give me a new total map that works like this. Given a key x, if x is less than the pivot, look in M1. And if x is greater than the pivot, greater or equal, look in M2. Okay? So that's just a way to glue two total maps together at a particular pivot value. So let's glue A and B together that way. And then let's take that map and update it at key K, so it should map that one to V. All right, that's my abstraction relation. Is it correct? Who knows? Let's see what we can prove about it. Right? It's not that the abstraction relation can be correct or not. It's can we use it in a proof to prove some properties of the data structure. So let's take our example tree. What was example tree? It was this one, right? That maps 2 to V2 and 4 to V4 and 5 to V5. And let's prove that it relates to the example map. What was the example map? It's an exercise. Make a total map that maps that way. All right? So then proving the abstraction relation between the example tree and the example map is left as a homework. So you can do that homework problem after lunch. Now, here's the kind of thing we need to prove about each of the operators of our binary search tree. We need to prove that the empty tree relates to the empty total map. How do we prove that? Let's remember what ABS looks like. All we have to do is apply ABS E that relates E to the empty map. That was trivial. We don't even have to remember the name of ABS E. We can just say constructor. Okay, we need to prove that the, let's see, if tree T relates to contents CTS, right? So this is its total map. And if we look up K in tree T, we get the same as if we look up K in this total map CTS, right? That's what it means to prove sort of correctness of the lookup function. And since that's your job in the search trees homework, these two things are really the most interesting things to prove about binary search trees. That related trees and maps give the same answer on related values. Okay? What do we have to prove for the insert function? We have to prove that if we have a tree T that relates to a total map, contents, and we insert K binding to V in T, and we update contents at K with V, that this relates. All right? That the abstraction relation is preserved under the operation. All right? So you can prove that too. Let's see. We have to do that for every operator of the interface of the abstract data type. So what were the operators of our interface? There was empty, lookup, insert, and elements. So we've got to do one more. We've got to do elements relate, that if T relates to the total map contents, then what? Well, elements T has to relate to elements of contents. But contents doesn't have an elements function. What is contents? It's a total function from nat to v. And to do an elements function on that, we would need to be able to compute what's in the domain of that total map, or in particular, which domain values don't map to the default. And that's not computable in general. So we'll express the abstraction relation for elements in a different way. Given a list of key value pairs, EL, let's calculate a total map by inserting every key value pair using tupdate. So calculate the list to map of the rest of the list, and then update that at key I with value v. So that calculates a total map out of an association list. And then our correctness criterion for elements is that if T relates to contents, then if we take elements T to get an association list and turn that into a map by this list to map function, then we get that total map. Now, I said that the abstraction relation itself, which definition you chose for it, is not part of the specification of correctness of binary search trees. But this theorem is part of the specification of correctness, and in particular, this definition is part of the specification of correctness, right? The interpretation of what this means relies on this definition. So this definition had better be simple and obvious enough that you can believe that it's the right thing. Okay? So who believes that this is reasonable for a definition of how elements should behave? You've got to raise your hands, because we don't have an alternative here. Okay. So now we just prove elements relate. Okay. So let's see. Why do we believe this works? Can somebody explain how this proof is going to go, just informally, before we prove it in conc?
You're going to need functional extensionality?
We'll need functional extensionality. That's true. That's fine. There are certain elements in the tree, right? The elements function, remember how it worked? It called elements prime to do this traversal of all the elements, consing everyone in order, right? The abstraction relates the tree to the total map. Who can formulate this? Raise your hand if you can give an attempt at formulating this into an actual informal proof. Yes?
We prove this claim by induction on the abstraction.
Okay.
If the abstraction is empty, then T is necessarily empty, and the elements of T will be the empty list.
Okay. So the explanation starts. We prove this by induction on the abstraction. So abs is an inductive proposition. We will have abs above the line as soon as we say intros, so we can actually do induction on it, and it won't work. And it won't work because the theorem is false. So here's a statement. Not elements relate, which says not for all T and CTS that if the abstraction holds, then the elements are what we want. All right, so let's prove this theorem. This is a fun little theorem. Let's do intro. to assume that negated thing were true, and now we have to prove false. So let's define a bogus tree T with 3 in the left child and 2 at the root. Why do I call this tree bogus? Yeah.
Violates the ordering.
It violates the search tree principle. 3 is greater than 2, but it's in the left child of 2. All right. Does it type check as a tree? Yes. Coq accepted this just fine. So now, let's let the map M be the update of the empty map at 2 with V. So there's no 3 in that map. And let's let M prime be, well, we'll do this combine operator on this tree. Okay, so I have M and M prime. These are different trees, I think. I don't know. And then we're going to assert the following. That list to map of elements bogus equals M, and list to map of elements bogus is not equal to M. And from that, we will attempt to prove false. Shouldn't be too hard. So how do we prove this side? Well, it will be, one of these will be proved from the assumption H0, and the other will be proved from the semantics of elements of bogus. Okay, so this is a homework problem. All right? Basically, the abstraction relation tolerates bogus trees pretty well, and the elements function has a different interpretation of bogus trees. Okay? And so therefore, the abstraction relation and the elements function disagree about bogus trees, and it's no surprise we can't prove this theorem.
So you need a well-formed...
We don't want to deal with bogus trees, do we? We want a way to prohibit bogus trees. And that's called a representation invariant. It's a property that a well-formed representation must satisfy to qualify as a binary search tree. Now, when we program in some reasonable programming language that supports data abstraction, like, I don't know, ML, Java, whatever, how do we enforce representation invariance? We make the representations private to the module or object class that implements the abstract data type. The client is not allowed to forge data structures, to build data structures that don't satisfy the properties. The only part of the program that can build data structures of that type is the private methods, the public methods of the object that can access the private variables, if we're in Java, or the inside of the sealed module, if we're in ML. So programming languages have mechanisms to enforce that only certain parts of the program are qualified to build these data structures. And if you can implement those parts of the program correctly so that they only build data structures that satisfy the representation invariant, then you're protected against clients, because clients aren't allowed to build things. All right, so we're going to express the representation invariant right here. So, what do we say? What's the representation invariant of a binary search tree? At each node, the key there is greater than the keys of all the nodes in the left subtree and less than the keys of all the nodes in the right subtree. So there's our representation invariant. We define for all nodes as a predicate on trees that applies some other predicate on trees to every node in the tree, right? So P is applied to this node, PLKVR, and recursive